When we think about the area of a triangle, especially a right triangle, the calculation is one of the simplest examples of geometry. It is simply base times height divided by 2, right? This formula works because a triangle is essentially half of a rectangle. Imagine you have a right triangle where the base is 4 units long and the height is also 4 units. To calculate its area, plug the values in this formula to get the answer as 4 times 4 by 2, or 8 square units. Now, this simple formula is possible to derive for simple shapes with straight lines and clear boundaries, like triangles and rectangles, etc. But what happens when the shape isn't so simple, like a curve? How do we calculate areas in those cases? We don't have a direct formula for those cases, and this is where calculus comes into the picture. Real-world problems often involve more complex shapes that don't have straight edges. For example, imagine a U-shaped valley, which is similar to the graph of y equals x squared, and you want to find the area of the land beneath that valley. For cases like these, geometry alone doesn't help. This is where calculus, specifically integration, comes into play. Integration is a fundamental concept in calculus used to find areas under curves. The key idea is to break a complicated shape like this one into tiny, manageable parts, like very thin rectangles. Then, for each of those rectangles, we calculate the area and then add them up. But how do we do that? For that, just imagine slicing this parabola into very thin vertical slices, almost like we are stacking pieces of paper next to each other. Each of these slices has a tiny width, and each slice is so thin that it looks like a rectangle. Okay, for example, I can approximate this parabola as a collection of these rectangles, right? Assume each of them has a width of 0.2. This is indeed tiny, so how many of these rectangles will be needed if our parabola extends till x equals 2? We need 2 over 0.2, or 10 such rectangles, right? And these x values will be 0.2, 0.4, 0.6, and so on, till x equals 2. Now, in order to calculate the area of these rectangles, we need base and height. Base is this, so we only need height. Tell me what will be the height of these rectangles. Yes, you are right, it will be this. But what is this value? It is the y value of this parabola, right? And that y value is equal to x squared. So the height at these values of x will be 0.2 squared. At this, it will be 0.4 squared, and so on, and here it will be 2 squared. I have made a table of x values and their respective y values. Now the area of this rectangle will be base times height, or this. Do it for all of these rectangles and sum them up to get this. So the area of this parabola will be approximately this, isn't it? See how cleverly we have approximated the area of this parabola by just approximating it as a collection of rectangles? Now, what if we make the width of these rectangles so small that it is impossible to see it with our naked eye, and we call that width by a variable dx, such that this dx goes to 0, very small width? This will make the parabola as a collection of billions or trillions of those rectangles, so almost infinite technically, and thus it will give an excellent approximation of the area of this parabola. Don't you think so? So if you understood what I told you right now, that means congratulations, you have understood integration, because that's what it's all about. Assume for this parabola at some value of x, we have the height of this rectangle as x squared. So the area of this rectangle will be x squared times its width, or dx, and then we sum all of these areas, which will be this summation of x squared times dx. And the value of x goes from 0, right here, up to 2, right here. This is what is called integration. Now, for very small values of dx, which goes to 0, instead of showing the summation symbol, we replace it with this s-looking symbol and write this 0 and 2 here. So the area of this parabola, or for that matter, any curve, is shown using this integration. And without going into much technical detail, the formula for integration of x to the power of n is given as x raised to n plus 1 divided by n plus 1. Now let us use it to calculate the actual area of parabola. Value of integration x squared dx will be x raised to 2 plus 1 over 2 plus 1, or x cubed over 3. Now to calculate the value in numbers, write x cubed over 3 minus x cubed over 3, and put this x equals 2 here, and here put this x equals 0. This will turn out to be 8 over 3, or nearly 2.67. See, it is so close to our calculated value using 10 rectangles. Isn't this cool? Therefore, if you look at integration in future using this way, you will never be scared of it, and it can never, ever intimidate you. Okay, now going back to our case of right triangle of base and height equals 4. We can represent it by this curve, y equals x, where x goes from 0 to 4, and its height, that is the y value at x equals 4, is also 4. So we can calculate its area using integration like this. Integral of x times dx from x equals 0 to 4. We get this is same as x raised to 1. So the value will be x raised to 1 plus 1 over 1 plus 1, or x squared over 2. Now write it as x squared over 2 minus x squared over 2, and put x as 4 here, and x as 0 here. This will give us 16 over 2, or 8, which is the same as what we get using the formula for the area of the right triangle. That is simply awesome. Before we go, let me tell you that integration has thousands of real-life examples, like engineers use integration to calculate the amount of material needed to build curved structures like arches or bridges. Then the economists use it to measure total income when graphed as a curve of earnings over time. Then physicists use it to find areas under graphs representing motion, like velocity versus time, to calculate distance traveled, and so on. See, it was not as hard as you assumed. It takes a lot of effort to make videos like this, and if you really enjoyed this explanation, then I simply request you to like this video and share it with others. And if I get 1,000 likes on this video, then I will make a part 2 of it, which will be much more interesting than this one. So good?